The other side of this is not internal flows, but I still want to go over just the look of what we're trying to describe is, and that is this boundary layer effect that occurs. So if you have a little boat sitting in the water right now, right, kind of coming in, there's these streamlines that are just totally parallel. And then they encounter this boat sitting on the dock. Not sitting on the dock. We have this boat just sitting in the ambient water. And if you were to trace these, there's deviations that occur because this thing is sitting in the body. And one thing that, it's because there's a deviation in this velocity. So there's a whole velocity field that we're describing because we have a coordinate system. It's the same picture you can always draw, right? And I can draw a vector to each one of these points, and it's just going to give me one velocity vector. But when I experience the body, what happens is you see these streamlines deviate across it. But then after a while, if I were to just not look here, it's it looks just the same as it did back here. So a big quantity that people look at is what is that? How large is that distance for these streamlines to return to this parallel flow look, right? So this is a very extreme one, just because it's a boat. But just sort of it's just that distance where, you have changing velocity vectors, and they just stop changing past this point right here. So that distance away from a body is something called a boundary layer. The boundary layer being out here, viscosity doesn't end up mattering. This is the inviscid part of flow. And then if you're here, this is the viscous part of the flow. So getting this number is critical to all external flows, because this number helps you then calculate forces happening on the body. So things like skin friction is a big one that we calculate.